In this video, we're going to talk about how to parameterize the boundary of the cone x squared over 36 is greater than or equal to y squared plus z squared, where 0 is less than or equal to x is less than or equal to 2. We're going to parameterize both the sides and the base. We're going to start with the sides, which is we're going to mostly be interested in the equation x squared over 36 equals y squared plus z squared over 4. That's going to be the sides giving me this nice cone shape. The base is going to be a circle, and the circle is going to be what happens when x equals 2, when it reaches this boundary point. We're going to worry about that later. A key idea to keep in mind is that whenever I have something squared plus something else squared, I should be trying to use my Pythagorean identities to make that simplify nicely. What do I mean by that? Well, that means that when I'm trying to come up with what my y and my z coordinate are going to be, a good place to start is to put a cosine of t and a sine of t in there. Because, as we see with this cone, there's actually a lot of circles here. So actually, there are ellipses, and we're going to get to that. So there's a lot of ellipses here, so we should probably have something resembling parameterization of an ellipse showing up somewhere. One thing I do want to note right now is that we see that these circles actually get bigger along the boundary of the cone. So to represent that there's going to be circles of different size, let's add another parameter s. And we're going to figure out what that's going to do after we've played around with this a little bit more. So let's see where we're at. If I were to plug in just this into my equation, I'd get y squared. Well, y squared would be s squared cosine squared of t. And then z squared over 4 would be s squared sine squared of t over 4. Uh-oh, I don't like that. I want to add something to this parameterization that will cancel out that 4. The way to do that is to add a 2 up here. So if I add a 2 up there, then there will be a 4 up here that cancels out. And then I can just use my nice Pythagorean identity to get an s squared here. So we found out that this side simplifies to s squared. Now I just need to figure out what to make my x component so that this is also s squared. So we need x squared over 36 to turn into s squared. And the way to do that is to make x equal 6s. That does the job. You also could have done negative 6s if you really wanted to, but that's okay. Either one works. And negative 6s would just be a little bit backwards. So we have these parameters here. And this does the job. If you plug in 6s, s cosine of t, and 2s sine of t into this equation, you'll get the same thing on both sides. We also kind of have this general rule that you'll notice that I had a 6 squared in the denominator here, which meant I put a 6 out there. We had a 2 squared in the denominator here, which meant I needed to add a 2 here. That's a general rule that we can use a lot. So keep that in mind as you're working problems like this. But we also need to figure out what s and t are going between. I know that t is going between 0 and 2 pi because it's basically representing going around in a circle. So we need to go all 2 pi radians. That's that. What about s? Well, I know that 0 is less than or equal to x is less than or equal to 2. But x, we're parameterizing as 6s. So we have that 6s is between 0 and 2, which then is going to give me that s is between 0 and 1/3. So that finishes off our parameterization there. Next, we need to think about the base. The base is going to just be a circle located, actually it's going to be an ellipse again, but it's going to be an ellipse located roughly at, at exactly x equals 2. And And we're once again going to be thinking about circles. So what are we actually looking at here? How could I describe this? This is where x equals 2, and if I look at my equation, that's going to be 4 over 36 is greater than or equal to y squared plus z squared over 4. This inequality is important because if I didn't have it, it would just be the boundary of the circle, but we're also interested in everything inside this circle too. So, since we are interested in everything inside, we want that inequality, and that's going to inform some of the stuff that we do here. I could rewrite this as 1/9 is greater than or equal to y squared plus z squared over 4. And there's a few different ways you could handle this. I think the way that I want to handle this is I would like to get one of my sides to just be 1. That would be kind of nice. So yeah, I'm going to let this be 1 is greater than or equal to 9y squared plus 9z squared over 4. And I am going to rewrite this in a very silly way. I'm going to rewrite it as y squared over 1/3 squared plus z squared over 2/3 squared. Why does that help me? Because now we're ready to do our parameterization, and it's going to be very similar actually to what we did before. First of all, what's my x going to be? Well, x is always 2 here. Once again, I'm going to have circles in my y and z component, so let's start by writing cosine of t and sine of t. And once again, I'm actually going to have a bunch of circles of different sizes, because you can think of this as having the circle of radius 0, or just the point on the x-axis. And then we also need to account for another circle that's slightly bigger than that, and another circle that's slightly bigger than that, all the way up until we get to the circle, or actually the ellipse, that is our boundary. So, since I'm going to have a bunch of these, I'm going to have an S to represent that there's actually like a bunch of ellipses going on here. Lastly, earlier we saw that we needed to put some extra things. We needed to put a 2 here and a 6 here because we had some stuff in the denominator. We're going to do that exact same thing here. I'm going to stick a 1/3 in front of my y component because I have a 1/3 squared in my denominator. And I'm going to stick a 2/3 in my in my z component because I have a 2/3 squared in that denominator. Now, let's go ahead and do what we did earlier. Try plugging in this stuff for y and z. There's nothing to plug in for x here. What we end up with is 1 is greater than or equal to 1/9 s squared cosine squared of t over 1/9 plus 4/9 s squared sine squared of t over 4/9. We see that all of those cancel, and we end up getting that 1 is greater than or equal to s squared. And you might say, that's not equal. But what it does do is it tells me what values of s I'm going to have in my parameterization. So earlier we had s was going from 0 to 1/3 because we were kind of going along the x-axis. But here I'm actually going to have s is going between 0 and 1 because I'm going outward from the x-axis. And where did I get that? I got that from here because I needed s squared to be less than or equal to 1. I needed to get all the different radii, and again I'm using the word radii because these loosely because these aren't actually circles. I need to get all those different radii up to 1. As for t, it's going to be exactly the same because once again it's just representing how far along the circle we're going, and since we want the whole circle, we're going to have 0 to 2 pi. So there we go. We have a parameterization for both the sides and the top, and in both cases we found out what the s and t values are going in between 2. So there you go. That's a few different parameterization problems relating to cones.